We continue with graph features, and now let's talk about link features. Okay, so our features have the form FUV. UV are nodes, and I remind you that V and U are not necessarily connected by an edge. They are not necessarily neighbors, and in fact, it is important. It is an important case when they are not connected, because one of the reasons we apply machine learning, or one of the use cases of machine learning, is to predict or identify missing links. Okay, so it is actually important. And I'll show, like in the previous part, several features, examples of features, and these can be used together and so on. Now, for a start, whatever we produced for nodes, we can use as link features. Okay, if you have the features of U and you have the features of V, then the features of the link UV is the, say, the concatenation of the features of U and those of V. So that's something you can do. Okay, there are features that are based on common neighbors, and these are especially useful when you want to predict future links or missing links in social networks. Okay, a simple one is just the number of neighbors, right? And you can also normalize it by saying, uh, take the common neighbors, okay, and divide it by the total number of neighbors of VNU. This is actually the Jacquard coefficient of two sets. The intersection of the sets divided by the size of the union of the set. Okay. Now, generalization or a variant of that is the Adamic Hadar index, where you basically count the common neighbors, right? W is a common neighbor, but you penalize the contribution of a neighbor W if it has many neighbors of its own. Okay, so you penalize it by you divide its contribution by log of the number of neighbors. Remember that W has at least two neighbors, so this is well defined. Okay, so that's another measure. You can also look at distance-based features. Okay, well, simply the distance itself is an example. Take the distance, the length of the shortest path between U and V. Now, one can say, well, the shortest distance is fine. However, we do want to distinguish between cases when there are many shortest paths or, just occasion one, two shortest paths, many versus few. Okay. And if we're looking at multiple shortest paths, what about paths that are slightly longer than the shortest path? Okay, that's also possible. This leads to the Katz centrality index, which is defined as follows. We basically sum up over all the lengths of paths, the number of paths of length L between U and V, and with each of these numbers is multiplied by some parameter a coefficient that has an exponential decay, beta to the power of L. KL is the size of the path. Okay, so basically, the idea is that we sum up the paths and we penalize the paths for being long. And this is something that was used already in the 50s or proposed by Katz in the 50s for measuring the influence of an actor in a social network. Okay, and so if you have many paths, then you have a high score, but the impact diminishes with the length of the path. Now, question is, what do we do with this infinite summation? Okay, uh, how can we compute it? Does it even converge? Okay, and these are good questions, and there's a nice trick that we can use. So let A be the adjacency matrix of the graph G. Now, you can easily verify that if you multiply A by itself L times, then the ijth entry is the number of paths of length L between the node Vi and the node Vj. This is fine. What it means is basically that the CATS matrix with the entries CATS Vj, Vi, Vj is basically the infinite sum of beta to the power of L, A to the power of L. Okay, how does it help? Well, under certain conditions, you can show that this infinite path, but not starting from 1, starting from 0, is this infinite summation is equal to I identity minus M to the power of -1. This is true if M is a square matrix and its eigenvalues are smaller than 1. Okay? Uh, in absolute value. Okay, so if you want to compute CATS, you basically need to take this part, I minus m to the power of -1, and subtract what we get for 0, which is the identity. Okay, so basically what we require is that beta is smaller than 1 over lambda, lambda being the largest eigenvalue of the adjacent matrix A. Okay, so that was basically it, a list of link features, and you can practice them by looking at this graph for example, understand what are the features that we would extract for U and V, the shortest path or the distance, the number of shortest paths, common neighbors, normalized atomic hadar, cuts, and so on. Let's talk about graph features, okay? And we discussed again several techniques. I remind you that we are looking at undirected graphs and the techniques generalized to directed graphs and label graphs. I'll say something in the end about label graphs and heterographs, okay? So the basic thing is the degree distribution. Okay, let's understand what that means. Take a list of degrees. For example, all of the degrees in the graph, or all of the possible degrees, say up to the number of nodes, and you can produce this feature vector where dig, the ith entry, is the number of nodes of G with degree I. Okay? So in this degree distribution, you say for every degree, how many nodes of G have this degree. Okay, so for example, we have this graph here. We say, okay, there is 0 nodes of degree 0, 1 of degree 1, 2 of degree 2, 1 of degree 3, and so on. So these are features that we can get from the graph. Now, the next features that I'll describe generalize the degree distributions. Okay, one is going from edges to graphlets, like we saw in the case of node features. Okay, so what does the degree distribution tell us? Tell us for every number j, how many nodes participate in precisely j edges. Okay. Now, instead of edges, we can have a list of pointed patterns, okay, for graphlets. And now, basically, we can produce for every pattern n number j, the number of nodes of G that participate in precisely J occurrences of the pattern. Okay, participate means that they are mapped to isomorphic induced subgraphs H, and V is mapped to the orbit. Okay, I remind you, this is from the previous part. Okay, so if you have a degree bound K, then the GDD, graphlet degree distribution, is really a matrix with P rows and K columns, where in the I, L entry, you have the number of nodes V, where the GDV, the number of occurrences of the graphlet HI, is equal to L. Their number of subgraphs is L. Okay? Now, that's a lot of information, and you can say, okay, what do I do with that information? Well, you can use all of it. So, for example, you can vectorize the rows, like take the concatenation of them, or you can sum up the columns, or take the average of the columns to get some measures of how frequent is each graphlet in the graph. Okay? And finally, we can also use the Weisweiler-Lehmann graph features. It's called a WL kernel. Okay, and basically, what you can do is the following. First, we want to realize, or I want you to think of it for a moment and understand that at different iterations, you get different colors. Okay, the color sets of iteration I is disjoint from the color set of iteration J, if I is different from J. Okay, and you can prove it by induction on I. This is actually pretty simple. Now, look at the following. If you count the nodes that receive the color 0, then you get the number V, because all nodes get the color 0 at the beginning, right? K0 of V. Now, each color in the first iteration, I equals 1, actually corresponds to a unique degree of a node. Okay, because the color is determined by the degree of the node in the first iteration. Therefore, the count distribution for the level 1 colors is actually the degree distribution. Now, you can then generalize it and say, let's have a predefined sequence C1 to CL of colors, and then the feature vector that we're going to produce is the vector N1 to NL, where Nj is the number of nodes that were assigned the color Cj in the execution. Okay, so that's basically it. That was the module 2, where we talked about tabular data, how we do machine learning on that, features from relational databases and features from graphs. Some takeaways. So we looked at tabular data, and their machine learning is closest to classic machine learning once we encode values as numerical vectors. Boosted variants of tree ensembles basically are strong baselines for learning over tabular data. And we talked about this important example of XGBoost. When we talk about relational databases, we can generate features automatically by composing projections, joins, aggregation, and we saw these examples in SQL, and we also talked about this Akora system that implements that. Okay, and when you look at graphs, then there are well-established techniques. They extract graph features based only on the structure of the graph. We talked about node features, link features, and graph features. And again, I will say that when you have heterographs, then they come with their own features, and you can combine the graph features with the features that are already given as part of the graph. And that was it.